gotta go over this real quickly. Zoom doesn't consistently show me whether it's recording or not. It looks like recording. And I never know what to look at. It's different depending where the cursor. Another little flaw. Anyhow, we're looking at integrals in polar coordinates. Okay. Now we started by saying if you do an integral in earlier chapters, just the integral to find the area of a region like r equals cosine theta, or theta from 0 to pi over 2, which you should be familiar with. Kind of looks like this. Maybe it's a circle, maybe it's not. You know how to prove it. These green regions are triangular, approximately triangular. You know, you got some curvature out here, but it's approximately triangular. And if theta is very small, then the angles out here are both pretty much right angles, so that the arc distance here is pretty close to the altitude of a triangle whose base is equal to r. And that would be for any r between here and here, because as you take the limit, these things get thinner and thinner. Doesn't make much difference which radius between here and here you use, or which theta between here and here you use if you use a theta. So this is an approximate triangle for small delta theta. It's nearly isosceles, so it's nearly a right triangle since theta is small, both its angles are nearly right angles. The area would be 1/2 base times height. And the base would be your r of theta, that's this distance, or for some sample point. And your altitude would be close to the length of the arc, which by radian definition is just your radius times your delta theta. So we get this, and this is just review. That's to give you a little context. That's review, something you did a couple of changes over. Okay. Now, if we have theta or sigma of theta, a density that's sigma 1/1 plus r. Okay. Then we'd be talking about a density when r is 0, the density be 1. When r is 1, density be 1/2. R is between 0 and 1. R is 1 out here, it's 0 here. So the density would be like 1 here, 1/2 here. So it's getting less dense as you move away from the order. If we want to get the mass of this region, then what we have to do is we can't just use these triangles because the density varies drastically between the origin and the far point of the triangle, especially for the triangles that have large r's. Okay. To get the mass, if this is a density, we would integrate the density times the area inputs. Okay. Now, why would we do that? Because we can break this thing up into increments, like this purple increment here is an approximate rectangle. Now, the r changes are pretty much doubles here, so it's not really, it's much closer to the trapezoid, but it's not even that. Okay, the way it's drawn. But remember, if your r's and delta r's and delta thetas are very tiny, then this thing becomes almost a rectangle with dimensions. What? Delta r, that's from here to here. And then r delta theta, which is the arc distance. At any sample point, at any r between here and here, you can choose randomly, arbitrarily, any r. And as you take the limit, as your delta r's approach 0, it doesn't matter which r you chose, it's all going to converge to the same thing. Now that's an idea you need to work with a little bit, but that's believable in terms of what you know from first year calculus. Okay. And if we talk about mass, then we can say that the mass instrument, the mass of this that's closing this interval would be theta evaluated at some sample point times your area. So theta delta A. I'm glossing over this a bit, but so your total mass total integral of sigma with respect to area is defined as a sum of your mass contributions over all these increments, which is the sum of your theta times your area, your delta M. Theta times your delta A, where your delta A, your area increment, is your R star delta theta delta R. So there's your mass times your area. Again, this is one dimension, the radial dimension of your increment. This is the dimension perpendicular to that dimension that's actually an arc length that's approximately straight for small delta thetas. Okay. So this approaches the integral theta, sigma of theta times R dr d theta. In the case of this region, R would go from 0 to theta, to cosine theta. R is 0 here, it's cosine theta out here at the boundary, and theta would go from 0 to pi over 2. So there would be your integral. It's an easy integral. It's one that looks a little weird. So to think, well, if you just let u 1 plus r, then r equals u minus 1, and you're integrating u minus 1 over u with respect to u. And that was easy to integrate. It's going to give you a natural log, then you're going to have a natural log of cosine theta, and that's a little harder to integrate. Maybe impossible. Okay. But that's what you would get from this density function. Then I just kind of pictured it in the interpretation where instead of interpreting this 1 over 1 plus r function as a density, you interpret it as an altitude. So now you have your curve down here in the r theta plane. You have an altitude of 1 out here, altitude of 1/2 here. As you move along this curve, the altitude goes from 1/2 up to 1. Think about in detail about why. As you move from this point to this point above the polar axis or the x-axis, if you want to look at it that way, you're going to go from r equals 1 down to r equals 0. You can think about what the curve would look like. I just kind of drew it any old way. And then you get this kind of curve flat. Okay. And the same integral would then correspond to the bottom. So, because each delta A would be the base of a chunk like this. Okay. Here's your delta R. Here's your R delta theta. Here's the surface above. Okay. You take a typical altitude, sample altitude, here to here, multiplied by the area of the base. Area of the base is R delta theta times delta R. Area multiplied by altitude, you get a volume. Okay. Let's think back to what we did with these. And there's two interpretations of the integral for R. Okay. Imagine a spot. Spiral. Spiral R equals theta. Easy to, probably the easiest polar curve to draw. Okay. And it looks kind of like this. To make a table, let theta equal pi over 4 here, pi over 2 here, 3 pi over 4, pi here. Then R equals 0 here in this direction, pi over 4 here, pi over 2 here, 3 pi over 2 here, and pi here. Okay. And it should actually be, pi is twice as big as pi over 2, so the arc really ought to go ought to be 3 times as far from your axis here as it is here, twice as far here as it is here. Hopefully that makes sense. Okay. I want to move to regions in 3 dimensions. One reason I chose this picture of region in 3 dimensions. we could actually take this region as an example. Now, this is going to actually be in cylindrical coordinates. We can let R goes from 0 to cosine theta. It's just this region. That should be clear. D, we go from 0 to 1 plus R. So at any point down here in the plane, any point like in the region here, Z is now an altitude above the plane. And then theta can go from 0 to pi over 2. So let's just say you got a density R over R plus Z squared. And the mass is triple interval where theta goes from 0 to pi over 2. R goes zero cosine theta, just the same limits that we had here. And Z goes 0 1 over 1 plus R. Okay, can you see that? See it okay? And then what we integrate is rho, which is our density. I just arbitrarily chose R over R plus Z squared. And now our limits 0 and 1 over 1 plus R. Limits on Z. That's it. Yeah. And 0 to cosine theta, well, same as it is here. Those are the limits on R. But we're going to use our RD theta here. Okay, because dz times RD theta is an altitude times an area, which is a volume. This is volume. Okay. Now that's jumping a little bit ahead, because that's actually in cylindrical coordinates, so we're not going to worry too much about that RD theta right now. You're not going to have to know that for a triple integral at this point. But since I've done this example, hopefully this idea of describing this region by describing the region in the plane where r goes from 0 to cosine theta and theta goes from 0 to pi over 2. And then for any point within this region down in the plane, we have an altitude. So z goes from 0 to 1 over 1 plus r. Then I just invoke some probably unrealistic function for density. And I can set up a triple integral. Now let's be a little more rigorous about it. Just think of density again. Let's just say our density is z over x plus y. And since our region might include x equals y equals 0, we don't want a 0 in the denominator, I'll put a 1 on there. Okay. Okay. If rho equals this in the rectangular region, x from 0 to 2, y from 0 to 4, z from 0 to 1, well, we can easily sketch that region. X equals 2 on this line. Let's say y equals 4 on this line. I should be a little further out. And z equals 1 up here. Well, we go up to an altitude of 1 above each of these points. We get this rectangle solid, right? That represents the region for x from 0 to 2. Here's x. Y from 0 to 4, it should be a little wider. Well, and z from 0 to 1. Not particularly well drawn to scale. This thing. There's our rectangular box. Then typical region has volume. Has dimensions. It's sloppily written, but it's dimensions. This. So dimensions are delta B equals delta X, delta Y, delta Z. Okay. So the mass contribution of a typical increment is rho evaluated at a sample point within the increment multiplied by the volume of that increment. Does that make sense? Now let's be specific about what this increment is. Okay, so I'm going to have a delta x and an x star. So the delta x here's a line x equals x star. Just somewhere within this delta x region. Now, this is going to be one of many regions down in the x axis or in the xy plane, strips of with delta x. Okay, this is a typical region. It has a width delta x and it has some x within this strip. So what we're going to do is we're going to call this delta x sub pi. X equals x sub I star. With me so far? And it's like our regions go from region 1 up to region N. Maybe there are a million of them. I can't draw them that thin. So I have to draw it a little thicker. Okay? So here's our x-axis, here's our delta axis, here's y. And then here are going to be a bunch of y increments, right? So let's just say that this one right here is a delta y sub j. And here's a line y equals y sub j star. Make sense so far? We're going to find that blue chalk. It's brand new. Here, be a region delta A sub ij and that equals delta x sub I times delta y sub j. I sure wish I could look at this thing and know whether it's recording or not, but yeah, there it is. Okay. This has a sample point. Xi star, yj star. That's the point at which we from now choose to calculate our density or whatever it is that we're talking about. Okay. Now things get complicated. Well, it gets a little complicated. Draw if I have a z-axis. what I'm gonna do is I'm gonna just partition the z-axis. Okay. And I'm going to take a typical increment. Z sub k. That would be from here to here. Does that make sense? Now, what am I going to do with that? Well, I'm now going to come over this picture. And I've really got to add another color. A little bit aggravating. But I'm the one that put the chalk down, so I think I'll be aggravated. So, okay. Now, above this, I'm going to draw a rectangular column. Kind of a wireframe, you can see through it, but you see that, okay, I've got a rectangle like so. Does that make sense? Then we're going to have some coordinate z sub k star here. If I project this parallel to this line segment, I see I've got this little block of width delta z sub k, sample point having coordinate z sub k star. Now, picture didn't come out as well as it could have, but get the idea. So if I take this picture and bring it up here, I've got this rectangular box. Delta yj here, delta xi here, delta zk here. Somewhere within this box, I've got a sampling point. Let's just say the sample point is here, and this is above this point here. But here's my sample, but here's my xi star, yj star, zk star. So my question is, what's the mass of that region? What's the expression of the mass of this little box within this big box? What's the volume, and what's the mass? Okay. So, gee, I hope all that was on the screen while I did it. No. Okay, hopefully you could see this construction. You might not have been able to see everything to the very left. So, just again, we started by just drawing the delta xi. You can see that much. And then I have this blue segment, which is x equals x sub I star. Then you can see the y equals y sub j. Hopefully you can see this delta z sub k, but there it is on the z axis. That's our delta z increment. Right here is our z sub k star sample point, somewhere within that increment. And then the delta x and delta y increments give us this base of this rectangular column. And corresponding to this delta z sub k, we have a delta z sub k box here, a box of altitude delta z sub k, base delta x I times delta y j. And the sample point within this box is xi star, yj star, zk star. Okay, so we've just established that the volume is this, and the density is rho evaluated in our sample. That's the point, that's the reason why I sample. So delta M ijk is our mass increment, which is rho of xi star, yj star, zk star times volume delta xi, delta yj, delta zk. Now, in this case, the total mass of the original box is what? It's a triple integral. I'll do it in the order dz, dy, dx, where z goes from 0 to 1. Remember, we're back to this box. Y goes from 0 to 4, and x goes from 0 to 2. What's rho of xi star, yj star, z? Well, there's your rho of x, y, z. So this will be z over x plus y plus 1. And it's not difficult to see how to do that integral. You find antiderivative of this with respect to z, which would just be z squared over 2 with that rest of that denominator. And that's from 0 to 1. Since you have fixed limits on these things, everything is pretty easy. Okay. So as long as you don't run into difficulty with the integration, you've got to get some natural logs and stuff. Okay. Yeah, it might get a little hairy toward the end. but probably not because of the fixed limits. You've got a pretty easy interval that allows you to calculate this density. Then you can think about what this means. Like your density at the origin here in this box down here at the origin would be 0 because it's Z over, right? So the density goes from 0 up to the maximum as you go from the XY plane up to the top of the box. Good luck in the mention. You can think about where the maximum value of rho would be. It's going to be when Z is the maximum and X and Y are minimum. So that would actually be at this point where Z is 1, X and Y are 0, so your maximum density is 1. At every other point, the density function is going to give you something less than 1. Since the density is always less than or equal to 1. Okay, and at many points it's less than 1. Is less than the mass, not less than the volume. And the volume is 2 by 4 by 1, which is 8. So if you did this integration and got something that's not less than 8, and probably a good bit less than 8, you know you've made a mistake in your integration. Okay, well, we're not going to worry too much about this. What happens if this region is not rectangular? Let's say now our region is the upper half hemisphere. And it's above the XY plane. How do we describe that region? Well, in the XY plane, the circle x squared plus y squared equals 4. X equals x star. Let's see. Okay, now a lot of this wasn't visible, but it's pretty easy to see what it was. Let's make this thing behave, okay. Again, this kind of depicts a hemisphere. It's not very well drawn. It takes time to be too careful with this. We only got a few minutes left. It's x squared plus y squared plus z squared less than or equal to 4. It's above the xy line. It's the upper half of a sphere. In the xy plane, every point of this hemisphere is above a point of this circle, x squared plus y squared equals 4. This is a hemisphere of radius 2. This is a circle of radius 2. Okay, now if we got x equals x star here, then what does y equal here? It's a, okay. Let's just kind of make this dotted line solid while it's inside the circle. What's the y coordinate of the point where this x equals x star line? It's the circle. Well, it's pretty easy to figure that out. First of all, we could just let x equal x star and solve this for y. Even easier, we can draw this triangle here, knowing that the radius is 2. This part of the, well, this leg is x star, so that what we have here is the square root of minus x star squared. Now that's drawn kind of small, but we can just draw a right triangle here and determine what y is. At the point where this x equals x star line intersects the upper part of the circle. So y equals square root of 4 minus x star squared. I can do that with a simple triangle, and that's usually the way you do it, but you can also solve this equation for y. Down here, symmetry would tell you, but you can also get the solution. If you solve for y, you get y squared equals 4 minus x star squared. So that y is plus or minus the square root. So down here, y would be negative the square root of 4 minus x star squared. If you not have, need a bigger diagram, but we're short on time. Got a line y equals y star, then you have a point here. This point has coordinates x star, y star. So we can tell how high you've got to go to get up to this sphere. So I'm going to say if x equals x star and y equals y star, then z goes from 0 to minus x star squared minus y star squared, which you get by letting x equal x star, y equals y star, and solving for z. That's an x star squared, that's a y star squared. Z would equal plus or minus this. Since we're looking at the upper hemisphere, we ignore the minus because that would imply a point below the upper hemisphere. So the maximum value of z that you can get and stay within the hemisphere is the value of z that we get out when we solve this equation. I'm going to get some real quick here. Okay, the hemisphere has description. You have your x values, your x star values going from -2 to 2. If x is some number between -2 and 2, you get y going from negative square root of 4 minus x squared to the square root of 4 minus x squared. If you know x and y, then you know that z, well, we're in the upper hemisphere, so z starts at 0, and it goes up to the square root of 4 minus x squared minus y squared. If your density is rho of x, y, z, then the mass of the hemisphere full integral rho of x, y, z. Now, x has the fixed limits on the interval, so x is going to go from -2 to 2. Then y is going to go from minus the square root of 4 minus x squared to the square root of 4 minus x squared. So we'll be integrating last with respect to x, next with respect to y, and z goes from 0 to the square root of 4 minus x squared minus y squared. Unlike the case where we're doing a box with fixed limits on x, y, and z, where this integral went from 0 to 2, 0 to 4, 0 to 1, density times dz dy dx. Okay? The limits on x are from -2 to 2. That puts limits on y. Y has to go y has to be between negative square root of 4 minus x squared and the square root of 4 minus x squared. And then if we choose any y point down here and call that y star, then this point is x star, y star. How far do we go above this before we hit the top of the hemisphere? We can solve this equation for z. And we get these limits. We can also do it geometrically with triangles. Time doesn't permit us to draw that. We can then describe the region. X goes from -2 to 2. Y goes from negative square root of 4 minus x squared to 4 square root of 4 minus x squared. And z goes from 0 to the square root of 4 minus x squared minus y squared. So we set up the integral. The -2 to 2 doesn't have any x's, y's, or z's in it. That's the one we want to put first. And of course, we integrate that one last. So we put the dx there and so forth. So we have an integral that makes sense. Now, I do want people to get a good start on this third section, on the section on volume integrals. We're going to have to do a little bit more with it, and then we'll move into integrals in cylindrical and spherical coordinates. Do the best you can on as many of those problems as you can. Look at the examples. And we'll go forward from there.